Good afternoon, everyone, and welcome to Class 10 of the EE380 Computer Systems Colloquium. My name is John Wharton. I got email from Professor Allison last night that said, "Greetings from Beijing," and that was the end of the message. So I have no idea what he's doing there. I presume he'll be back soon, but again, I'm filling in for him today. Since this is the last class of the quarter, I'll have some announcements for some of you who are registered for credit for the class. The deadline for submitting the commentaries on the 10 classes is next Friday night, 30 seconds before midnight, timestamps and so forth. Beyond that, we will be accepting late submissions at our discretion, namely at Dennis's discretion. For those of you that were not in class last week, there was a bit of a shuffling around because of a combination of factors. One speaker cancellation, another speaker taking ill. We ended up showing a videotape of a John Hennessy talk. For people taking the class for credit, you have a choice of watching the Hennessy talk and submitting a commentary, if that's what you'd like to do. If you had already seen that presentation and would like to watch something else instead, feel free to do that. Or if Professor Hennessy's, I keep calling him Professor Hennessy. I guess now his title is President Hennessy. If President Hennessy's talk isn't something you want to hear, then pick something out of our archives. In the interest of simplicity, whatever it is you watch, just click on the same button on the class homepage where we have the commentary for the Hennessy talk and tell us what you really did watch. But procedurally, it's easiest just to go through the same procedure there. Normally, there's a policy of only accepting 2 virtual classes. You're expected to attend 8 of the classes live, and you're supposed to, or you're allowed to miss 2 without any ramifications, repercussions. Since last week's class was not live for anybody, we will not be counting that. Anyone who had already missed 2 classes, if you missed last week as well, that's fine. That will not count against your grade. Since this is the last class, I don't need to announce next week's speaker. I'll announce today's instead. Are you ready to go, Eliot? Yep. Okay. Today's speaker is Eliot Miranda, who has been involved with the Smalltalk community for many, many years, spanning a couple of hemispheres. He worked at Park for some time and joined Park Place Systems in 1995, has been working on various optimizing schemes. His abstract is posted, and quite frankly, much of this went over my head, so I would do a bad job of summarizing it for the audience. Eliot Miranda, thank you very much.
Thank you. The microphone level's okay? So what I want to talk about today is what's been happening over, I suppose, 2 decades of research and development in late-bound execution architectures, late-bound object-oriented programming languages. Most of it done, in fact, at Xerox PARC and here at Stanford, and lots of the people are here in the audience, which gives me great pleasure. So you have to understand that I'm going to get this wrong because the people who did the work are sitting here, and so I quake in fear. And Sun Micro, another offshoot of Stanford in a way. Towards the end of the talk, in the last quarter, I'm going to talk about some new work, which is my attempt to respond to my august predecessors with the limited resources that I have at my disposal. So the talk's going to talk about Smalltalk VM evolution, a little bit about the language. I'm going to assume that most of you in the audience haven't actually seen Smalltalk, and certainly won't have seen a Smalltalk-80 system. Well, a lot of the people here will have. We're going to look at the self work, which is the real meat of the sophisticated optimization technology, which is now actually on a lot of people's desktops. And then I'm going to talk a little bit about the Smalltalk commercial world as an explanation for why I have reduced resources at my disposal. And then finally, I'm going to talk about this new work. So Smalltalk is a vision of the computer as a medium for self-expression. We all know that computers are fantastically powerful business tools, but they're also creative tools. And at the time when Xerox PARC that when the Smalltalk group at Xerox PARC formed, computers were large, smoky things in back offices that really didn't work for ordinary people and were extraordinarily expensive. And they had an amazing humanistic vision of the computer as something that everybody could use and benefit from. And their model of who to target was the kid. Children as people who are impatient, selfish, short attention spans. If you can make it work for them, you can make it work for everyone. And a huge aspect of Smalltalk is the delight in the fun that comes from playing with systems. Well, if you're going to have a medium for self-expression, programmability is key, because unless you can actually make the system behave as you want, you are a slave to what's on the machine. So it's really vital. And so language comes to the fore, because it's through language that you express yourself to the machine. And so if you're thinking about designing a system which is to be of self-expression, it is something that the user will extend. And the user will have to explore the system. So a language that supports extensibility and supports comprehensibility is vital in addressing the goal of self-expression. And the original concepts, I think, in Smalltalk come from people's experience of what worked, what was relevant in terms of modeling. Alan Kay had experience in the Air Force with early attempts at data abstraction, which impressed him. Del Goldberg brought in work on concept formation from the child psychologist Seymour Papert. And that ended up in an object-oriented programming language, the first truly object-oriented programming language, which from a computer science perspective is interesting in terms of supporting modularity, polymorphism, abstraction. You can think of an object as a virtual computer. So an object gives you all of the power that you might expect from a computer, and the ability to hide things, arbitrary things within it. But from a psychological point of view, there's this really nice paradox that objects are at once abstract and that you can do what you want with them. But on the other side, they're very concrete because they have this parallel to how at least some of us think. But the thing that is most radical, I think, about the Smalltalk vision and the thing which much of the industry misses and has left behind, except maybe at the GUI level, is that the language design follows from a human-centered design, a vision a humanist vision of what we might do to make people's lives better, more enjoyable, more productive. And from that starting point, a very, very radical and original language, and a very, very radical and original set of implementation technologies came along. And the lab did a number of language design cycles, then taking the language out to their test audience and bringing it back, refining over the years. And the first Smalltalk that I really recognize as something very much akin to modern Smalltalks is Smalltalk-76. And I don't know if you can see the URL, but the paper, Dan's paper, is available on the web now. And this introduces modularity in terms of objects hiding their state that are only accessed through messages, which also is this notion of computation as communication. You send a request to an object, you don't operate on its internals. It's concerned with the business of how it achieves that end and returns some result to you. The language also, at this stage, provided inheritance, so that a class which defined the code of an object could be extended by creating a subclass and adding just new behavior in the subclass to derive some new object that was a small part away. And 76 also provides the ability to add to the system a method at a time, a class at a time, so well away from batch-oriented compilation, supporting experimental programming for the first time, and allowing a person to develop an understanding of the system and augment it in one step. The computation as communication naturally supports a notion of polymorphism, where different objects can respond to the same request in different ways, giving you very, very powerful facilities like a really nice mixed mode arithmetic library where fractions and points and integers can all be sent the same arithmetic messages, but respond to them in their own ways. And that gives you a lot of reuse because it allows you to apply code that sends a particular set of messages to any set of objects that understand those messages. But another very radical thing in 76 is the use of reflection. You can see three different kinds of reflection. You can see the ability of objects to describe themselves and display themselves so that you can use inspectors and the like to look at their contents and explore them like that. But at a deeper level, the computational objects in the system, classes and methods that define the code of the system are themselves objects, and they are themselves defined in the system. So one is able to extend the language because the language self-definition is within itself at the same level, and you have this seamless ability to extend the system as you go along. And a really interesting element is that execution state is also reified as objects. So when you send a message, which is like a procedure call, the procedure activation is actually available to you, the programmer, as an object. And the stack you can think of as a Lisp-like spaghetti stack of chained objects. And this allows you to do very powerful things because now you have a way of, at the language level, using your same semantics, your same object-oriented programming language, to implement novel control and to extend the system's control notions. So later on, you'll see things like people implementing exception handling systems entirely in Smalltalk with just one tiny bit of VM support. And the quote that I like from the Smalltalk 76 programming system is, choose a small number of general principles and apply them uniformly, which really helps in terms of comprehensibility. There's less to understand. The more powerful the principles are, the more reach you give the user, the better their amplification of their abilities. So okay, let's finally get on to some computational stuff. Smalltalk 76 and 80, their execution architectures are based on the notion of a byte-coded language and a virtual machine to execute the language. There's a very simple compiler which parses from source text to program nodes, and then one pass over the program nodes to generate bytecode. And you're talking about a compiler of about 2,000 lines of Smalltalk, maybe not even that much at that stage, but very small, very concise, very, very comprehensible. And in the paper, I think I spelled syllables wrong, but there are basically 13 opcodes. An object is a thing that has some instance variables, and it has an identity, and the code that's wrapped around it needs access to literals and messages and global variables, which refer to the classes in the system. So you see being able to load the receiver, load and store temporary variables, loading constants, loading and store global and instance variables. I think I've missed off instance variables. Jump and jump conditional, which we'll return to in a bit, and then send and return. And one of the really nice things about Smalltalk 76 and 80 is the elegance of the VM design. There's an interesting paper by Peter Deutsch in the Green Book, which is Smalltalk-80, Bits of History, Words of Advice, a series of papers on early Smalltalk implementations, which contrasts the Smalltalk-80 VM with the Interlisp D VM, and makes pointed criticisms as to the Interlisp D VM's lack of separation between the system and the VM, and the use of platform-dependent code at the system level to implement parts of the system, Whereas in the Smalltalk-80 and Smalltalk-76 VMs, you see a very, very strict separation, really nice modularity. And one of the, I think I can come to that later, is primitives. We'll come to that later. Anyway, the challenge from an implementation point of view is that given that your system is built out of messages, and that every message send that creates an activation actually allocates an activation record, a context for it, there's a very high send frequency, and there's a very high context allocation and deallocation frequency. And sends, because we have polymorphism in the language, actually involve searching the class of an object for the method that it has in response to a token, a selector, which names the message to invoke. And that process recurses up the class's hierarchy following the inheritance hierarchy. So sends can be very, very slow. So there are three basic optimizations, very important optimizations in Smalltalk-80 and 76. The first is to inline 8 basic control structures, if true and if false, which are the Smalltalk equivalents of if and if then else, while false the basic looping construct, and to inline them and not reify the deferred code that would be the arguments there. I'm going to go out at this point and try and demonstrate what I mean by this deferred execution. So in Smalltalk, if I was to create a piece of code, I can create this thing, and this is a thing that can be used later. This is something that I can evaluate, and when I evaluate this, it just returns the string. This is code. I do value size, and find it, and I can reuse this piece of code as many times as I want. So what I've done is I've just grabbed what's a lexical closure, and I'm holding on to it in an inspector, which allows me to have a look at it, and I can send it messages and evaluate it as many times as I want. And the way that we would do if then else is like this. We send a message to the result of some expression. Let's actually send it to the object true instead. So we're going to send if true, if false to true, and true is going to know whether it's true or false, and it's going to choose whether to evaluate the first argument or the second argument. And so if I do this, we get this is code, which is great. But when I did it, you noticed that a little prompter came up, and it told me that in fact the argument to if true is not a literal block, and this compiler really likes to inline literal blocks, and Dave is quite rightly shaking his head in horror at this. But we'll come to that later. We will. So let's have a look. In the system. Oops. And have a look. And we see that we've got 3 implementations. One is an abstract implementation that says subclass has got to do this, and then we have the obvious one, which is that in false we evaluate the false block, and in true we evaluate the true alternative block. So control structure has been subsumed within message polymorphism, and we no longer need separate control structure, and we have it as part of the language. But that does mean that we have costs, because every time we do a conditional, we're actually notionally creating 2 closures, doing a dynamically dispatched message send, and evaluating one of the closures. And that has a significant performance overhead if implemented naively. Therefore, in Smalltalk 76 and Smalltalk 80, the compiler chooses a subset, not all control structures, only the basic ones, and compiles them to bytecode, which uses conditional jumps. That gives you a rather interesting thing, that if I was to go 1 if true, okay, false, oh dear, I'm going to get an error because the bytecode that evaluates conditional jumps expected to find a Boolean, and it didn't. It found an integer. And instead of the system being clever enough to send the message to the small integer object and allow it to do what it would, instead we got a must-be Boolean error. Yes. Okay. So now the other major optimization is static receiver type prediction. You know, the bytecodes, even though there may only be 14 opcodes, we have 256 bytecodes, and so the opcodes are distributed amongst the bytecodes according essentially to their static and dynamic frequencies. You want to use the encoding to make methods nice and compact. But you can also do things like choose a subset to represent very commonly executed methods that have very common receiver types. And so the messages that do arithmetic and comparison are implemented in the bytecode interpreter to check whether or not at the point of send there are in fact integer arguments, and to do them in line to alleviate the send. Right, that's a good point. So the implementation of message lookup is to represent the set of messages by a set of unique strings called symbols. And by keeping the symbols unique, it means that we can use address comparison instead of string comparison to check. In fact, that's a major optimization that I completely missed out. Thank you. So sharp is a sign which is used in Smalltalk to precede various kinds of literal. And sharp followed by just one of the binary operators or by a word gives you the symbol, which is the same thing that you would use for a message send. So down the bottom where there's these messages, this would actually be a symbol lookup in hierarchy of. So then the other major optimization is the first level method lookup cache, which is to attempt to shortcut the lookup through the class hierarchy. And it's a very simple algorithm. Imagine that objects, either by virtue of their position in memory or hidden in a header field, have a hash reasonably randomly assigned. We just take the hash of the selector and the hash of the class of the object we're sending the message to them, and derive a probe into a cache which holds class selector method triples. And if the class or the selector match and the selector match, we've found our method and we return it. Otherwise, we have to go look up. And with a cache size of about 1,024 entries, you get something like 93, 94% a hit rate. And this must be worth factors of 2 or 3 at least in the execution performance. So this is probably one of the most significant. But the other thing that I really like from the Smalltalk 76 paper is Dan's quote here, which is that programming Smalltalk is fun. There's this feeling of immediacy and power. Things are at your fingertips. They respond nicely. There's also this emphasis on graphics and the visual, and it's enchanting. It's more than just fun. It's enchanting. Okay, so the work was in Park was lucky enough to have pretty sensational resources by the time of the time. In the early 80s, the researchers were using the Dorado microcoded machine, which cost $100,000 in 1980 dollars. Was a 17 nanosecond cycle time ECL machine. It generated so much heat, it was in a room of its own. There was a big room of them, and cables ran to displays. And this thing just about ran Smalltalk acceptably. So getting it out into the world, as people wanted to leave Park, set up a company to commercialize this technology, it was very, very difficult. But at that time, the 68K was coming about, so you could see, you could say that it was a 32-bit micro. There were some workstations around, the PERC, the Sun One, and there were people who were implementing slow interpreters, like myself. The Dorado executes about 300,000 bytecodes a second, and my first VM did 30 bytecodes a second. So there were some very slow interpreters out there. And then I don't know the exact. I've only heard this obviously third hand, but I hear that one day Butler Lampson was talking with Peter Deutsch, who'd done the Dorado Smalltalk implementation, and perhaps sneeringly, but probably not, said, "Come on, that polymorphism you spend all of this time doing, it's almost never used. Come on, all the time, it's the same old message." And the light went on for Peter, and he realized that, okay, if it is the case that polymorphism isn't ever used, that one can afford to cache lookups in machine code by arranging that ascend is represented by a native machine code call with a cache tag to allow the target method to check whether what's been called is appropriate. The problem here is not in the speed of the check; it's in the cost of the miss. But we'll come back to that. Another thing was to eliminate contexts and to map context to stack frames by using native machine code and native call return. It would be much more convenient to use the machine's native stack format. And so there's a scheme which still provides context, but this is done by a lazy mapping scheme. So not until you try and access an activation record as a context is an object created for it, which means that in the vast majority of executions, just as polymorphism is almost never used, contexts are almost never used. So most of the time they're not paying for it. The point very strongly to make there is that when you do use it, you really, really do appreciate it. And if you don't have it, then there are all sorts of other discombobulations that you have to go through if you don't have those facilities. One of the nice things is that mapping is facilitated by the strong encapsulation of the object-oriented system. There are very few places in the VM where context might be accessed, and so it's very, very easy to insert the tests to provide this illusion of a stack frame as an object and map between one of the two. So the thing we're going to look at in the next slide is precisely how the cache lookup works, because it's interesting in terms of contemporary implementations of languages like C++. But one of the really interesting things about PS was that it was successfully entirely binary compatible with the image that ran on the Dorado Smalltalk, and that's a testament to the cleanliness of the VM design, the fact that one could take the same image and run it on a radically different implementation architecture with no changes. So the inline cache idea is what we're going to do is have a region of memory where we're going to maintain, rather like the real memory in a virtual memory system, native code versions of byte-coded methods. And whenever we do a send and find a byte-coded method that isn't present, we're going to translate it into machine code, which is something that everybody's familiar with now with JITs and Java. So when we translate a send, we translate a send into the loading of whatever the receiver is of the message into a register, and whatever the arguments, which I've omitted here. And then we want to do a lookup of a particular selector. So we're going to load a register with the selector, effectively its address. So we can refer to the thing. And then we're going to call a routine, a runtime routine, which is going to do what the old bytecode interpreter did. It's going to look in the first level method cache, and if it doesn't find things there, it's going to search the hierarchy. And what it's going to do is, if it only finds a bytecoded method, it's going to compile that bytecoded method to machine code, and then it's going to return that. If the machine code method is there already, it's going to return that. If it couldn't find memory to compile the bytecoded method to native code, it's going to scavenge that region of memory, and it's going to eject some of the methods, much like a paging algorithm. And then what we're going to do is rewrite the machine code such that the receiver gets loaded with the same value, but instead of loading the class with a class register with the selector, we load it with the class object of the first receiver. So the first time we send a message, we find an object, we find out what its class is, and we remember that class. What was the class we had when we sent this message? And we arrange to load that in this register, our class. And then what we're going to do is we're going to immediately call the entry point of the method, and that method is going to, in its entry point, check that the current class of receiver, which may or may not be the same, agrees with the actual class it was when we bound the send. So it's a runtime linking thing. And the entry point code looks like, examine the receiver and try and find its class. And there's a complication here because the system has immediate data. Integers are represented as tagged types for efficiency again. So we have to deal with the fact that we may be dealing with an immediate data. And in this implementation, I'm imagining that the least significant 2 bits are a tag that identify characters or integers. And if the tag is 0, this is a normal object, and I indirect through it to find its class. So after these first 2 statements, I have the class of the receiver or its tag pattern. And if that matches what's in our class, then I can continue. If it doesn't match, we've got some different class. We sent the same message to some different object. And then what we do is we go and do the old thing and find a new method and then rebind the call site. So there's this real cost in misses in that we actually have to go and relink the stuff. HPS is the second generation implementation of PS. PS was 68K specific and was implemented at the assembler level in a macro assembler implemented in Smalltalk. HPS had a number of other people working on it, including Dave Unger here. And one of the major changes it had was generation scavenging, which doesn't really affect code generation in that the previous system's deferred reference counting also avoided having to garbage collect the stack, but did make a major change in the field of the implementation. The PS implementation, in going from bytecode to native code, was very much like macro expansion and concatenation. So one of the things that you see in PS is no ability to avoid things like the reification of the result of a comparison as an object. If you compare 1 and 2, say is 1 greater than 2, in the language, that's going to yield either the true object or the false object. And if you do a conditional branch on that, what you're going to do is do a conditional branch comparing the top of stack against the true object or the false object. It's very expensive. What you'd really like to do is just do the comparison, load the condition flags, and do the jump. But PS couldn't do that. HPS does, and one of the planks of this optimization scheme is to defer the generation of operand access until you get to a bytecode which consumes some result. And the way you do that is very simply, as you scan the bytecode in the native compiler, when you see a bytecode that references an operand, you don't assume it exists. Instead, you put an operand descriptor from it in a simulated stack. And then when you get to actually produce the code for a send, the code that looks at the send can then look at the operands, say, oh, right, that's actually a literal integer. The 2 arguments are a little integer. I can inline it, or whatever. And in that way, generate reasonably efficient register-based code with registers for the arguments, because we don't actually marshal the arguments until we actually construct the code for send. And this was really cool, and Peter probably rightly thought that it was a trade secret. And finally, in 1998, HPS was done in 86, 87. In 1998, there was a paper from IBM Java VM, which described this technique for the first time. One of the things in the bytecode set, there is a new bytecode set to really facilitate this dynamic translation. And one of the things that's really important here, for example, is putting a no-op at the head of a loop. So at the end of a loop, you get a jump back to the beginning. And that's a control flow join, and that's a problem because your assumptions of what values were live when you came in are incorrect. They have to be modified by the jump back. And by having a no-op, which is always the target of any backward branch, the translator can avoid having to do a multiple pass over the bytecode and can just recognize, oh, right, this is a control flow. I have to flush my notions of what's live and can continue. But the other thing that's I keep on saying cool, I'm sorry. Another great thing in HPS is machine portability. And it's a highly portable system in a very, very simple way. There's an abstract to-address machine with some extensions, 3 address extensions to exploit things like the Spark. And that's implemented as C macros. So there's an instruction like cmove RR and takes some arguments, and that is expanded dependent on a processor-specific file into the actual native machine code. And that's how compilation works and how portability is achieved. It does mean that one is mixing C and assembler, which is vile, but it works. And then the other thing is that HPS added unwind protect, which is the ability when we do a non-local return to catch the fact that we may be going through a catch block, some block to ensure some action that's always executed on leaving. And once you have unwind protect, you can then implement exceptions in Smalltalk. At this point, I'm going to go back to. No, I better not. Okay. So the extraordinary thing about HPS is that it was the fastest VM around for almost a decade. And in fact, commercially, it was the fastest VM around for more than a decade, but not Smalltalk VM. That's right. Well, it's very important that in fact, the Stanford guys beat it. What saw was faster, and the implementation of Smalltalk in Self was faster, and both of those came within 10 years. But neither of those were commercial efforts. So it is quite extraordinary that this machine was the fastest around for 10 years. There were lots of other efforts going on at the time. Dave did Berkeley Smalltalk, which was very popular. It was one of the earliest freely available Smalltalks. Tektronix did an assembler level 68K virtual machine. Lots of us in Europe, got the blue book describing it and had great fun. And my own were called Brouhaha, and they crawled at first, and then they kind of staggered. And then some very much more interesting and relevant work for what we're going to be talking about later on is the Dave Unger's thesis. I think it was your thesis. No. SAW. Which was Smalltalk on a RISC, as a very nice piece of RISC-oriented design, of very strictly looking at features and only including features which paid for themselves. And that lives on in the Spark in terms of the Spark's register windows and support for tagged arithmetic. At the University of Illinois, there was some work on typed Smalltalk, which was, I think, less successful. It depended on concrete type information, extending Smalltalk with a very low-level notion of types to help the optimizing compiler and producing 68K compilation. And I'll return to the issue of types, but a kind of structure-based concrete types are very antithetical to a highly polymorphic system and really interfere. So this was a slightly paradoxical thing to do. There's also a Digitalk VM for OS2, which compiled to native x86 code. There was a screamingly fast microcoded Smalltalk V board. Smalltalk V is a Smalltalk by Digitalk. So started up in the mid-80s. That was in 1988. And out of Carleton University, Dave Thomas and his team set up a company, Object Technology International, and they did 68K based implementations which ended up in Canadian defense missiles as control units, and actually may or may not still control many Tektronix oscilloscopes. So already back in the 80s, this is a practical language which has absolute definite industrial applications, and it's not this researchy prototype that people think it is. Okay, troublesome types. If you look at all systems other than type Smalltalk, these systems attempted to deal with the language as it is now, but type Smalltalk required type information to generate good code, and the kind of type information it needs is very concrete, and Smalltalk programmers naturally are thinking very abstractly. They're thinking about this polymorphic system. And there's a real mismatch. And while there are abstract type systems, certainly in the early 80s they were extremely hard, and they really only applied to quite toy scale systems. And the Smalltalk system was already very large at the time, so being able to apply polymorphic type systems at the time wasn't really on. And the other thing is that if you have type information in your program, it's about defining the fixity of your code. And the compiler can obviously use the fixity of the information and what that implies about its fixity to generate efficient code. But if you're doing exploratory programming and you're trying to develop new algorithms, etc., you're going to be breaking the validity of that type information all the time. You're going to be changing the system. And so there's this really basic mismatch between the two. Peter Deutsch, who did the execution architecture in HBS, was trying to make HBS go faster in the late 80s, early 90s, and did so by providing a set of primitive operations that assumed their argument types. So it would assume, that there was 2 integers. There would be an add operation that would assume if there were 2 integers and not do any checking. This is obviously much more efficient than the abstract operation, which has to check whether there are integers. But the problem is how to get the type information to generate them. So nothing was actually released. Then we get to self, and now my terror grows. So self is Dave's design of Dave and Randall Smith's design of a language to be even more comprehensible than Smalltalk, and to discard a number of things in Smalltalk, in particular classes and metaclasses, which have their proponents but also their complexities. And self is based on the notion of prototype objects, and being able to have an object which depends on another object, which is its prototype, and to define its additional properties, just as in Smalltalk-80 we can create subclasses. But in self, we also support state inheritance. There's no direct access to slots. Instead, all state is accessed through messages, and that means that you can actually share state variables in ancestor objects. And the other thing that David did, was why he was shaking his head earlier, was eschew the optimization of assuming that a certain class of messages applied to basic control structures, and instead allow it to optimizing compiler technology to try and inline when it was possible. So self was even harder than Smalltalk-80 to make efficient for those reasons. Well, the first really significant attempt at I think, implementing self efficiently was the Self 90 and 91 compilers, which are described in Craig Chambers' thesis and some other papers. And this was an attempt to do much more aggressive optimizing compilation when generating native code. And the problem here was how to derive type information. One of the techniques is customization, which is the idea that when a method is found, instead of running the common copy of the method, which may be in use by a number of sub-objects which share it, that the native compiler, since it's transforming this bytecoded method into machine code, can actually construct a customized version of it, which is only going to be used by that particular class of objects or that particular trait of object. And then the type of self is suddenly known. It's suddenly constant, and we can turn messages to self into unchecked calls. There's also an attempt to generalize the notion of type prediction, just as the Smalltalk-76 and Smalltalk-80 implementations predicted integer types. So the self-compiler, based on whatever type information around, would predict that a particular value had a particular type and put in a test, and if the test matched, could inline that code, and if the test failed, would call the more general method exactly like the static type prediction in the special selectors in Smalltalk-80. And performance was gained by using that type information then to inline and eliminate a lot of dynamically bound calls. There's also some range analysis on integer ranges. You know, at conditional branches, you can say, okay, well, if I'm less than this, that means that range of values is going to be in that range, and that can help you eliminate bounds checks and the like. And another thing that you can do is at a message send, which may have which may be polymorphic, which may have more than one type. Instead of just saying, well, okay, if I miss, or if I'm going to guess one way or the other, one can create a number of different copies of the code depending on what the type actually does, and so one splits the method along polymorphic sends and has a number of different copies of the code. Now, while this was really successful and did indeed produce significant improvements over Smalltalk, there were problems. There was a code explosion. Everybody in the world was really jealous of Dave and co. and their 32 megabyte and then 64 megabyte machines. We barely had like 2 megabyte machines. How do these guys do it? How do you afford this? Amazing. There were long compile pauses as this optimizing compiler would kick in and do its stuff. And also, performance was fragile in that small changes in the program could radically change the type information that the compiler could derive and create large changes in the performance of code. So this thing didn't really have very continuous performance. But work with Self found that even with all of this optimization technology, in fact, unsurprisingly, because of this optimization technology, the number one cost in say a program that was stable, that had been optimized, that is running, would still be method lookup and the rebinding of dynamically bound calls. And one notorious benchmark, Richards, has in it a loop which sends messages continually to objects of one of 4 classes, and every subsequent send would be to a different class and would miss. And if you profile your VM, you'll find out that that's where the time's going. You're doing all of these misses, and then you're going and you're munging that machine code to change it to call the next class, and then the very next send, you've got the guess wrong, and you go again, and you're spending all of your time doing all of that horrible work, flushing the instruction cache, etc. It's a nightmare. So the novel idea was to extend this inline cache notion to more than one tag. And so here, what would happen would be when your linked send misses, instead of going and rebinding, you're going to rebind the send to call a little dispatch table, which is going to have an extensible number of cases in it. And so here we've got exactly the same code we had before, but now we've got a sequence of class constant comparisons, and depending on whether we get a match, we can jump to the body of the method and skip the prologue checks. And the idea here is to allocate enough memory that you can have some small number of cases like 8. The first time you're going to end up with 2 cases, and then the next miss you're going to have 3, and then when you finally get to 8, you're going to give up and you're going to leave it, and hopefully you've got rid of a large proportion of your sends. That idea was really successful. 50% speed ups in the speed of Richards, and that was great. But the fabulous thing about this was the observation, which I didn't get, and a number of people just didn't get when we read the paper, was that inline cache, that polymorphic inline cache, is now collecting concrete type information. Right there, making your program go faster is precisely what are the set of types that you can expect. And so there's a quote at the end of the paper which I'll read. More importantly, polymorphic inline caches are an important source of type information since they record the set of likely receiver types for every send. The presence of PIC-based type information may fundamentally alter the problem of optimizing dynamically typed object-oriented languages, and that's what it proved. And it was great. This was in 91, and by 93 there was a complete implementation which was significantly simpler than the 91 system, which used polymorphic inline caches to supply type information to a compiler and produced better performance than the previous system. That is, I'll go back to that in a bit. With much simpler machine. The architecture there is to have a non-inlining compiler, which is very much like the PS compiler that just goes from self bytecode to macro native code. The important thing with that native code is to be able to have the place to put the polymorphic inline cache and maintain that. It's more difficult to maintain it in the bytecode. Once you translate it to the machine code, you've got the space in the machine code to store your information. And then the other thing is, well, when do we act on the type information that we're collecting? So the idea here is that by putting in invocation counters, we can measure what parts of the program are taking the time and only spend time optimizing those parts. And so we're exploiting the common observation that 95% of the time is in 5% of the program. So we have to do 5% of the work optimizing it to get the bulk of the benefit. And so code, when it's first executed, is compiled to quite a simple, crude machine code, which has PICs and counts invocations. And then when invocations trip a certain level, a simple inlining compiler, which is actually an optimizing compiler, is invoked. It can look at the stack, the set of activations. It can examine the type information in the calls and generate much more efficient code as before, using the same kind of optimizations as we used before, customization and splitting. But this time, not having to infer types, being actually guided by what the program's doing and having concrete type information. Because that concrete type information is not a future guarantee of types, it's only what we've seen in the past, we may have to plant type tests to ensure when we enter a block of code which is working on the assumption that they have these types, that the arguments actually do have those types. So if a type test fails, what do we do? Well, what we can do is, on the fly, dynamically de-optimize to allow execution to continue with the polymorphic code that we generated in the first place. And then later on, the code can be re-optimized based on the new type information in the presence of the new objects. In fact, dynamic de-optimization is generally useful. You can use it to recover from a type trap where the type's wrong and you need to run more polymorphic, flexible code. You can use it to enter the debugger when you hit a breakpoint. But the really important thing you can do with it is that you can undo any inlining of a method in native code that the optimizer has done when the programmer redefines a method. And so one of the significant new pieces of technology in the self VMs is the maintenance of a dependency network, which tells you where a particular bytecoded method has been inlined, such that when the bytecoded method is redefined, you can go and void those now invalid copies, going back and allowing the program to recover and get back to its optimized state. So the Self-93 compiler was more stable in terms of its performance. It had much more predictable performance, and it was significantly simpler, being 11,000 lines versus 26,000 lines of C++. And performance was, on the whole, a little better. There were circumstances in which it was worse, but on the whole, it was significantly better. Compile pauses were much improved, but they were still an issue, and dependency information was still a problem. And so they still needed big machines that none of us had. So that brings us up to.
If only you'd been patient, you know.
Right.
Pentium 4s with 4 gigabytes.
If only you hadn't been British and poor in the university. Yeah, I know.
You'd ever see.
Yep. Yeah, I hope we can crowd around and see Dave demonstrate Self afterwards. So this brings us to Anamorphic, a company set up by Dave Griswold to commercialize the Self technology in the context of Smalltalk. And David had been working on Wall Street and had been working with Gilad Bracha, now at Sun, who's a type theorist, amongst other things, building exactly the kind of polymorphic type system which allows you to type Smalltalk without constraining the way that you write Smalltalk, to allow financially, strategically important applications on Wall Street to be statically type checked. And so David was very familiar with the kind of performance problems that one had, especially with double arithmetic in Smalltalk implementations, and very familiar with the type issue. But he felt, having talked to, on talking with Hersley on the Self-93 VM, thought that it would be perfectly amenable to a really nice Smalltalk implementation. And Dave's not here. I was hoping he was here because I want to ask him permission to talk at a school, but I won't. All right. Never mind. So maybe later. The idea was to apply the Self technology to Smalltalk, which was commercially relevant at the time, and they managed to work for 2 years in complete secrecy. It's amazing how they did that. A group of about 8 people doing a complete ground-up Smalltalk implementation, a re-implementation of the type system, and a VM that had all of the self-adaptive optimization technology in it. This time, the base architecture was to translate bytecode to direct-threaded code, and then in the direct-threaded code put polymorphic inline caches and counters. And the direct-threaded code operators were generated on startup. And then the optimizing compiler would go from the direct-threaded code decorated with the type information to Intel machine code. One of the most important things that they did was a lot of work on how to represent the dependency information. So they were able to actually get their code cache down to a very reasonable size. Even though I say 1.5 megabytes here, I'm told that a lot of that was debugging and that they could run in 750K of native code. And when they turned up at OOPSLA, the performance was spectacular compared to the contemporary Smalltalk machines. And as you'll see later, I've been working at Park Place for 2 years and trying to work on faster implementations, and I remember being being really gutted seeing this beautiful system. It's screaming, and having done what I want to do, not in the same way at all. And one of the really interesting things that was happening, of course, exactly in the mid-90s, was that Sun's Java effort was happening, and the anamorphic team realized the relevance, and in their last year also did a Java VM, which contained much of the same technology. And that became the hotspot server VM for Sun. And it did mean that Sun paid $30 million for this company and their technology, and the Smalltalk companies didn't. And
it's also used in the hotspot client VM itself.
Right, but I hear that there's some significant optimizations have been left out of the client VM to avoid pauses. Okay, right. Okay, so both the server and the client.
I think the Self technology as being plus improvements they made being the base of hotspot server and client, and I think like a lot of other commercial Java VMs for desktops all use these tricks now. And then the server one just has a Mondo optimizing compiler.
Right. So my life was strange. I don't want to spend too much time on this, but this is relevant in that it explains how I find myself trying to compete with this technology without any shoes. hence the shirt. This shirt is the Parkplace shirt, not the Parkplace Digitalk shirt. Yes. Parkplace had spun off from Xerox with its Smalltalk technology in the late 80s, and around about 1990, I'm not sure of the exact time, a CEO was brought in who will remain nameless, who was brought in to take the company public. And from that point on, there started to be serious systemic problems in the company. One of the major ones was that marketing really didn't know what Smalltalk was. Smalltalk was this very, very broad spectrum language that was being used in mission critical and very, very profitable applications on Wall Street. It was being used in machine control. It was being used to control railroads. It was being used all over the place. And it wasn't something that you could sell very easily. It was this very, very complex, powerful technology that at the time seemed exotic. It was very hard to explain to people what was good about it. You had to go through a kind of a personal revolution if you'd come from the statically typed world to actually accept this stuff worked. There were all sorts of barriers to Smalltalk's acceptance, and none more so than those faced by the marketing arm of Parkplace, who didn't know what they had, but they wanted it to be Power Builder. They really did. And so the thing wasn't marketed appropriately. Engineering was told to dumb down their technology, exploit tiny parts of it in building front ends to databases rather than exploit its full power. And then the company misidentified its competition and merged with its closest technology twin, Digitalk, which had the Smalltalk-80 Smalltalk technology, and it tried to merge the technologies together. But the real competition at the time was, of course, Java, and misidentifying that was a really big disaster. And then for 2 years, the company tried to smush these two different technologies. The VisualWorks technology, which was the name that the Parkplace Smalltalk had become, which was cross-platform and portable, with the Digitalk technology, which was tightly, closely tied to the Windows platform, which had native GUI. Both were excellent technologies in their own way, and trying to bring them together was a real mistake. And then another extraordinary thing happened. This company was doing very well in services. If you think about the problem of having some extremely powerful technology to apply to computing problems, the customer needs help. They need help in education. They need help managing transition of their existing process to kind of process that an exploratory programming environment supports. Many elements, new approaches to design, etc., which imply that one needs a services business. One can have a very healthy services business going arm in arm with the selling of one's technology, allowing one's customers to understand the technology and exploit it better. And so Park Place had an executive who grew the services business to a point where it was getting more than 50% of the company's revenues. And at that point, NASDAQ started making noises about, but you're listed as a technology company, you have to be listed as a consulting company. And the board thought, oh dear, our stock price will tank. We're going to be competing against the likes of Anderson, against which we don't look very impressive, whereas we want this great technology asset. So the guy who did that was pushed aside, and the amount of money brought in by services was allowed to decline, and that, of course, had knock-on implications for the ability of customers to effectively use the technology. A number of small companies were acquired at that time. One was acquired so that Tim and myself and Hal Hildebrand could work on doing a fast VM to compete with Strongtalk and the Self technology. And the company was brought in, and Hal arrived, and management wouldn't let us start for a year, and things left. Yes, my right. And then the other thing was cannibalize and de-invent yourself. The company wrote a letter saying Smalltalk's dead, long live Java, which was a real way of shooting itself in the head. And it's called the suicide letter, and if you look up suicide letter on the web, you'll find it. It's probably at the top of Google. While the Smalltalk technology, which still had a very healthy customer base, was still going on, was not being given any new investment. Its revenues were being spent on a ludicrous attempt to attack the Java market at a time when all of the big players were using loss leader techniques to get market penetration. You could buy IBM's Java offering for $110 and get a $100 rebate. There was no money there. So lots of us were laid off. Finally, we got rid of the CEO, but we hadn't released new products for 2 years, so we were in trouble. There were other terrible things. When the suicide letter came out, the company said we're not going to continue supporting the VSC product, the Digitalk product. And the Digitalk product had most in common with IBM's Smalltalk product. And at the time, Park Place didn't have its own team tool for doing team programming. And the company that did provide a team tool for VisualWorks was OTI. And later in 1995, when this merger happened, OTI were acquired by IBM, handing VisualWorks customer list to IBM and allowing IBM to say, you see those guys who've committed suicide? But why do you come over here? And it was bad. So the life in academia was pretty good. Life in healthy companies like Sun was pretty good. Life in this company that had this great technology was just hell. It was absolutely crazy. There was a joke at the time, which is that a guy's walking down the road in the country, and he looks over a fence and he sees a three-legged pig. And later on, a couple of minutes later, he sees the farmer, and he says to the farmer, so I noticed your three-legged pig looked very nice. Had a lovely ribbon around its neck, a bell, and everything. He says, "Oh yeah, it's a very, very priceless pig. That is. It's lovely. Last year there was a fire in the house. Ran in the house, rescued my son, and a year later, my wife was driving the tractor. Tractor fell over. She was trapped. Pig went, got my wife, pulled it out from under the tractor before the tractor fell in the river. It's wonderful." Well, that's fantastic. That's why you take such good care of it. How come it's only got 3 legs? Oh, you don't eat a pig like that all at once. So, you know, Visual Age was IBM's product, Smalltalk product. It was healthy, but they also had a services business. In fact, the services business is probably the most important part of their Smalltalk business. And it was starting to tout Java and ports to Java. VST, the old Digitalk product, had gone. VisualWorks, somehow, you know, they couldn't kill us. The customers kept on paying, and we were able to somehow recover. And I'm still here, and it's extraordinary. We did get to within weeks of shutting up shop, but it's still there. And Gemstone, which is a Smalltalk-based object-oriented database, you know, has recently gone the same way as Parkbase and decided to dump its Smalltalk technology and tell the world that it was going to do Java. And exactly the same things happened there. They can't wet the sponge there. They're still alive. The Java business is not really that important, but the Smalltalk business is still great. Their existing customer base is there. They canned the Java product. Oh.
Working on it because they found that the only money was coming from the Smalltalk product.
Right. I daren't say things like this unless I can really remember, because you know there's people watching. It's like show up in a court of law at some time.
Reference?
Oh, it's an obscene reference to electrocution.
Okay.
You have to wet the sponge that you put when you put the thing on the head. Otherwise, you get a burnt sponge. I'm sorry. It's a terrible sense of humor. Right. Sorry. So, okay. So now we're getting on to the new thing. Is this attempt to do this cool adaptive optimization technology in reduced circumstances? So. Right. Okay. Well, I'm going to try and go fast then. If you can give me 10 minutes, I can get it done. So, AOSTA, Adaptive Optimizing Smalltalk Architecture. You know, I like acronyms. What the hell? What's new now that wasn't new in '96? Well, maybe none of these things are new, but they're well understood. That you know, open source, there are a number of convenient licenses to put stuff out. Strongtalk was bought by Sun, but very kindly, Sun released the Strongtalk image and the virtual machine as a binary for people to use, and all of the code in the Strongtalk image is available under a FreeBSD license. And I wanted the type technology because I thought it would be relevant to VisualWorks, and asked Eli Bratcher could he maybe arranged for it to be released, and Dave was instrumental in getting it released, and lo and behold, we got the whole thing, which was really nice. Another thing is that hairy optimizing compiler technology and single static assignment form are well known and written up in very accessible books now, so even a clod like me has a chance at an optimizing compiler. And a very significant thing is that since '96, there's been, you know, Moore's law says between 16 and 25 times increase in processor speed. So the pause time thing is close to being a non-issue. You know, even if you weren't able to bootstrap your optimizing compiler, you might be able to get the same performance as, you know, in Smalltalk now as people were getting in C++ in '96. And then there are some things to reuse. The existing system is fantastically productive. Anybody who's used Smalltalk has this feeling both of fun and of being really productive. And I haven't been able to show you much of that today, I'm sorry, but it is widely touted as having 3 to 5 times the productivity of competing technologies like C++ and Java. The other thing is that Dan Engel's original ideas of reflection and reification are very important to the notion of how I'm going to do this. And then I was also lucky to have Peter Deutsch's optimization work in the VM that I work on, his Go Faster primitives, which have lain fallow with no means of generating that code over the year. They're still in the VM. And the secret weapon, I think, is the bonhomie of the Smalltalk and Self communities. Because of the vision Smalltalk has always attracted people who seem to be fun-loving and trusting, and I find it a really wonderful community. I'm proud to be a part of it, and so the ability to work with my fellows is enabled by that. So Gilad and I were talking over lunch and agreed that it would be really nice to do it in Smalltalk. But how? Well, the idea is to just do everything at the bytecode level and not do it at the hairy VM level at all, and to go from bytecode to bytecode that uses primitives that eliminate tag tests, and to do all of that inlining. And then one can make it easily portable because one's doing a bytecode to bytecode compiler, not a bytecode to native compiler. One doesn't have to do lots of different backends. But the other thing it enables is for the various members of the Smalltalk community to get a fast VM without having to get a common VM. So if it's possible to do a portable bytecode to bytecode optimizer, it's possible that people can take their existing technology base, extend it to have more performance, and all move together, rather than having to agree on a common VM. And so then that to be a stepping off point for actually getting a binary standard and allowing us to collaborate. So one of the things that I want to emphasize here is that the technology in AOSTA is not radical. It's definitely a reuse of lots of existing ideas. But its rationale is not from a pure technology perspective. It is from doing things like attempting to allow that Smalltalk community to reknit and refocus and move forward. I do want to show you one thing, and that's Hobbs up there. A really influential thing was a good colleague of mine, Vasily Bykov, doing a Smalltalk-80 implementation in Smalltalk, and seeing how that was very practical. For the VM implementers here, they'll know that their work at the microcode level and at the C level was painfully difficult to debug, and it was really hard to do a VM in shorter than 6 months, and production quality systems would take a year plus. Vasily did his first Smalltalk-80 implementation in 3 days. And this is Smalltalk-80. This is the system as it was in May of 1983. This is the system that Steve Jobs saw and took to go do the Mac implementation. And this is a Celeron. This is a 400 megahertz Celeron, 460 megahertz Celeron. It's not even a fast machine. Smalltalk's great, it's got everything in the system here. I'm going to go and have a look at something in the compiler. And I want to go and have a look at the inlined messages. And I'm going to say explain here. And it's going to insert an expression which is going to tell me, allow me to get the value of this thing. If you can read this, this is if true, if false, if true, if false, if false, if true, and or while false and while true. And these are the set of selectors that the compiler inlines to machine code. And now I'm going to go and like browse everywhere in the system where this is used. And so I'm going to have a look, and I'm going to look in here. And you'll notice, perhaps, maybe people in the audience can see it easier than people out there, that this code here, while perfectly readable, doesn't have temporary variable names. It just has effectively just numbers, the temporary variables, because this code is being constructed by decompilation from the source code, and there isn't actually any source code in the system. But the source is out there, and what's really interesting is that the source is in a disk. It's actually, because this is now, the disk doesn't really exist. It's actually just an OS file, but Smalltalk at this stage in its development was basically an operating system, and the file system is part of the system's code. So you could run it without a file system, or you could run it with a file system. And so what I'm going to do here is just, I'm going to initialize the file system so I can get the source code. Oops. Now, if that happened in your standard VM, you'd be in your machine level debugger, and you'd be hosed. But here I've got a debugger, and it's telling me that a message isn't understood. So, okay, we'll have a look here. And it is that we're sending this starting at replace elements in from to this Smalltalk-80 byte object, and it doesn't understand it. Okay, so let's define a body for this in anticipation of actually being able to implement this, and then let's have a look at implementers of this in the system. And ooh, byte array, that looks good. Let's grab that. Okay. That looks pretty good. So let's paste this in here. I notice here that in fact there is a byte array in this Smalltalk-80 byte object. This is a wrapper around the raw bytes. So I'm going to replace this self here with bytes, and I'm going to accept this method, and I'm going to proceed, and my Smalltalk's working. So it's a lot easier to do these things in Smalltalk. And when I finally saw this and realized that, yes, if you could implement a VM in a language like this with the environment to support you, you could be hugely more productive. I realized I had a chance with my reduced circumstances to do an implementation which would be competitive in terms of its overall execution speed. And Hobbs was one of the things that really persuaded me that it was feasible. I should say that the experience of the anamorphic group was that to do an implementation of a C++ dynamic optimizer of a production quality is sort of a 3 to 4 person year activity. And even after anamorphic's technology being bought by Sun, it was another 1 to 2 years before it was released. So being able to do a production quality release of that technology in C++ is probably 5 to 10 person years of effort, and not something that I could complete this decade given my resources. So the architecture is to do a minimal augmentation of existing VMs and to do bytecode to bytecode optimizing compilation, and to go from bytecode to static single assignment form and do some analysis and inlining, and then generate optimized bytecode. But to move as much of the complexity and housekeeping, that dependency management and all of that stuff, out from C++ up into Smalltalk. Also, a central idea is the ability to, as I've just demonstrated, develop it at the Smalltalk level using the interactive debugger, etc. So to augment the existing VMs, you need to add some kind of invocation counters. And I'm going to skip the details here, but it turns out that conditional counters have a really nice property in that if you count conditional branches, they occur with less frequency than sends, and they measure basic blocks. So if you're measuring invocations, every time you activate a method, you increase a count. If that method is shared between 2 different call sites, it's ambiguous as to which call site has the higher dynamic frequency, because they share a single counter. Whereas if you count conditionals, you get basic block information, and that tells you all of the sends in a basic block. So in adding conditional counters to the current Smalltalk VM I have, I only lost 10% of compute performance. The next thing to do is to remove the static.
We really do need to be winding down. The class ended 10 minutes ago. Is there a way to
I have 2 slides.
wrap this up? Okay, thank you.
I have 2 slides. To remove static type prediction so that you don't have information as to whether a particular send of plus was to integers or not hidden. Because if it was to integers, the static type prediction will have eluded that send, and the information won't be there. So you actually remove some optimization. and you need some introspection on your bytecode methods so that you could send a message to the bytecode method and the VM can provide you with the cache information in a convenient form so that the compiler can have a look at it. And the next thing you need to do is to arrange that when you jump back into Smalltalk, when one of these invocation counters trips, is the ability to freeze that set of code, because that's the code that you're going to study and optimize. And you need like a second space of code to be able to run your optimizer in. So let's skip that. There's extraordinary low-hanging fruit in terms of what's the speed-ups available. If you can do loops that avoid bounds checking and avoid the tag checking involved in the induction variable on a loop, you can get speed-ups of 3.5 times. You can get similar speed-ups if you can batch instantiation and instbar assignment to have initialized instances. And if you can combine those kind of optimizations with the inlining of blocks for the non-inline control structures, you can see orders of magnitude speed-ups. And we've enabled, this enables us to move lots and lots of complexity up above the line. So the compiler or the optimizer, dynamic de-optimization, dependency management, the decision as to when to throw away optimized methods if we're using up too much space to represent optimized methods, the heuristics necessary to apply this relevantly, can all be done in Smalltalk, and none of that has to be done in C++. But there are some great benefits. So one of the cool things is that it's suddenly easy to turn off the optimization. So imagine you had an animation application which wants to be optimized but doesn't want ever to be interrupted by the optimizer kicking in. Well, it's really easy to train the application and then deploy with the optimized bytecode and the optimizer discarded. And for similar reasons, it's easier to deal with periodic code like background processes which kick in occasionally, which a traditional optimizer would see as low frequency and not necessarily optimize. Last rather bizarre notion is that you might actually be able to patch the optimizer dynamically in a running program and boost your performance by tweaking it. Okay. So I'm done. I want to thank Dan for very much for your architectural ideas, which I hope I'm going to exploit really, really well in this. They're brilliant. Thank you.
Thank you very much, Eliot. In the interest of time, we'll have questions, but we'll end the class officially and then take the questions offline.